Awesome. Great. So I have been asked to give you an overview of mitigation methods for stellar spectral variability in RVs. And given that we've already talked a lot about different mitigation methods in this session and previously, it's a little hard for me to give you an introduction to mitigation. But I hope that with this talk, we can kind of take a step back and contextualize what different methods exist and how can we think of this problem in the big picture. So I'm legally and morally obligated to start with this plot. You've seen it before, blah, blah, blah. We have observationally, instrumentally, we're fully in the EPRV sub-meter per second regime, and yet the exoplanet detections haven't been emerging as we might hope. And the reason for this is no secret. It's the intrinsic variability of the stars that we're looking at. And as the EPRV working group wisely said, to address this, we must radically advance our understanding of the underlying stellar physics and its impact on RV. So the field as a whole has turned a lot of attention to this problem in recent years. It's obvious that we need to deal with this. This is just an overview of a few bright, heavily observed stars. And basically, the more we look at these stars, the more we notice stellar variability is the dominant thing that you see when you're doing an RV survey. And maybe you could say it's bad luck with these. Some of these are more active stars. But even when we go to one of the quietest stars we know of, and one of the ones that we should know the most about, the sun, we clearly see variability signatures. And this is a nice paper by Lily Zhao, cross-comparing between multiple instrument solar data sets. And it's a really powerful illustration that the instrumental stability is awesome for these. We're seeing tiny signals in the data, and those signals are coherent across all the instruments because they are from the star. So what are we really observing here? We've been over a lot of these things in the past days. We're seeing oscillations of the star. We're seeing granulation and supergranulation. We're seeing surface features like spots, faculae, plage. We're seeing long-term activity cycles. And I would sum it up by saying we're seeing astrophysics. So notice I haven't been calling it stellar noise. I've been calling it stellar signals because that's what it is. It's a signal for the star. It has a lot of interesting physics encoded in it. And I want us to think of mitigation methods here, not as getting rid of the noise, but as teasing out and separating multiple signals that are in the data. So with that said, I guess my main question to address in this talk is how do we model stellar variability in the spectra that we observe? And as I was putting this talk together, I thought I would choose a few recent papers that I thought had really interesting ideas or methods being developed here and go through some of them. But then I looked at these papers and I was thinking, actually, there's a bunch of other papers that also have extremely important ideas that contributed to this. And then I was like, well, wait, there's these papers too that I really want to cover. And there's also these papers. And then I checked the archive and even more had appeared. So suffice it to say, there's a lot of options out there in the literature for mitigation. And at this point, I have a giant stack of papers, and in my attempt to put together a coherent narrative, I think I'm looking something like this. If you're curious and want some light reading, I did put together an ADS library of more than 150 papers that you can check. But suffice it to say, we don't have enough time left in this entire conference for me to actually go through all of the different methods and how they work. So instead, I wanted to find some way of kind of giving an overview, giving you a sense of what is out there and what we're working on without delving too deep into any given method. So let's start. Just kidding. I'm not going to judge and tier rank all of the methods against each other. We'll save that for the next EPIV conference. What I want... I do want to make the point also that even if we were trying to compare the methods against each other, it's really hard to quantitatively or qualitatively compare the performance of different methods because we don't really know the ground truth here. This is from the Extreme Stellar Signals Project cross-comparison of some benchmark star observations, same data analyzed by many different methods. And you're seeing not only is the RMS different across all of the different methods by quite a lot, but comparing one-to-one the radial velocity values gotten by each method, there's some agreement, but basically you run your data through a different method and you get a totally different time series. And we don't know which is the right one. So there's progress being made here in terms of using the sun as a benchmark test bed where we know the ground truth. But even then, there are so many different regimes in which we want to be able to do this stellar signal fitting that it's going to be hard to ever say, you know, this is the one method that's the best. So I want to go back to the initial question of how do we model stellar variability? And reframe it a little bit as how can we model stellar variability? As in, why do we even think it's possible to tease out the signals of the star from the signals of the planet? And I have tried to distill a few different themes that I think are reasons why we have hope of being able to resolve both of these signals separately. And these themes are things that really underpin as assumptions many of the methods we're using. So the bulk of the talk, I guess, will be going through some of these kind of themes in the efforts of stellar signal mitigation. And the first one I want to start with is the symmetry or asymmetry of spectral features. So a Doppler shift is inherently symmetric. Stellar signals are not symmetric. On the left here, you're seeing an image of a spot crossing, and you notice that in the residuals here to the best fit, or to the plain old Gaussian line shape, basically everything is strongly asymmetric unless you get lucky, unlucky, and see the spot at exactly the center, the disk center of the star. We also heard from Michael Palumbo earlier that granulation is inherently asymmetric, that the line bisectors contain a lot of information about convection and that they change over time as granulation changes. So all of the signals that we're looking at are a little different from a Doppler shift due to true center of mass motions of the star. And that provides a basis for a lot of the different methods that we use. I could put a lot of methods on this slide, but just as a sampling, one of the classic approaches here is looking at the cross-correlation function bisector and trying to detrend that against radial velocity. This goes back to the early days of RVs. I think even the idea even predates actually finding planets with radial velocities. Some more recently developed methods include looking at shape changes in the autocorrelation function, which is a translation invariant version of kind of the average line shape in the spectrum. This is the Scalpels model developed by Collier Cameron et al., which does a kind of data-driven PCA type approach to changes in the ACF. And finally, the Fiesta model moves into Fourier space and uses the fact that when you do a Fourier transformation, all of the asymmetric information is contained in the phases in Fourier space. And so we can kind of try to separate out symmetric and asymmetric and translational shifts there. Right. I think this idea of asymmetry in the line is closely tied to the idea that we know what a Doppler shift is. We might not be able to write down an equation for how stellar variability affects the spectrum, but we can write down an exact equation for how a center of mass Doppler shift changes the observed spectrum. So why not use that? One method that I was excited by recently was Yan Liang's AISTRA code, which is a neural network where she cleverly trains it by augmenting data to insert Doppler shifts and teach the model what a Doppler shift looks like, basically, so that it can then learn how to separate out non-Doppler shift things. There's also the idea of Doppler-constrained PCA, where you do a sort of data-driven learning of how the spectrum changes in time, but you explicitly require that it has to be orthogonal to a Doppler shift in the spectrum, and that removes the risk that you're going to eat up the planet signals here. You could think of this as kind of the I know a Doppler shift when I see it school of thought. So these work well, but I do want to put in one caveat here, which is that the stellar signals aren't entirely asymmetric, and they're also not entirely orthogonal to a Doppler shift. There's a nice kind of toy model demonstration of this in a recent paper led by Lily Zhao, where she shows for changes to the line shape. As expected, the line depth and the line width are independent of the radial velocity shift, but a bi-Gaussian representation of a skew can project strongly onto the RV shift. And more interestingly, I think, if we look at stellar models, so this is using the Phoenix model grid, if you change the effective temperature or the log G of the star, that is not independent of the Doppler shift that you measure. So we have to be careful in implementing these sorts of things in order to make sure that we're not leaving behind the parts of the stellar signal that get most tangled up with the Doppler shifts. The next theme that I want to talk about is using the wavelength independence of a true Doppler shift. So just like we know that a real Doppler shift is symmetric in the line, we also know that it's the same at all wavelengths, whereas stellar variability is not the same in all lines. We've been hearing a lot about this. So basically, if the RV change that you measure changes across the spectrum, it's not really a Doppler shift. This has given rise to things like chromatic radial velocity indicators, and I would tie this back to things that BJ was talking about earlier in terms of line-by-line radial velocities and chunk-by-chunk radial velocities, even order-by-order radial velocities. If you subdivide your RV measurements across the spectrum, you can then use that information to try and figure out how changes in the spectrum are localized. I would also put activity indices from different individual stellar lines into this category. Something like looking at the calcium H and K index is saying this activity information is localized to this bit of the spectrum. And this figure is just one example from a paper by Alex Wise looking for more lines that correlate with the chromospheric S index and trying to generalize that to using more localized activity indicators. Okay, my next theme is using the time coherence. So the first two themes were things that you could do with any spectrum, not knowing what the timestamps on the spectrum are. But we do know the timestamps, and we can use those. There are a couple of ways to use times. One is to average or bin over the stellar signals. And basically, every stellar signal is at some level stochastic. So if you watch the star for long enough, there will be enough randomness induced in the stellar signal that you hope that you can just average over it. This is what is used for dealing with oscillations, although it's not perfect. It's also, it can go into analyses that subdivide the data in time and try to check whether the signal is, whether the planet signal or the RV signal that you're seeing is coherent across the time of the observation. A nice example of this is the Welch's method for periodograms. Victor Ramirez Delgado has a poster on this, and you should go talk to him about it. The other kind of approach or school of thought to using the time coherence is to actually resolve the signals and model them in the time domain. So again, Gaussian processes have really emerged as king here. They provide a nice, somewhat more or less physically motivated way of parameterizing variability in time. And I'll talk a little bit more about how GP models are implemented a bit later. For now, I will point out that resolving time domain signals does require a lot of observational coverage. And it requires us to be a little clever about how we're scheduling our surveys. So I'd point you to this paper by Arvind Gupta, which uses a Fisher information approach to quantify how much data at what times we need in order to make a Gaussian process model work for various forms of stellar activity and actually enable us to pull out planet signals. Okay, related, I guess, to this idea of the star changing in time is the idea that the star is an underlying disk-resolved object, even if we're not seeing it as such in our spectrograph. So the way that we tend to model variability due to things like spots and faculae surface features is to generate a disk of a star, paint some features on, grid it up, and integrate over those to get a spectrum. This is what the SOAP method does. I'm also highlighting a couple of other methods, Starry and Spotter by Leonel Garcia. These two aren't as fully featured as SOAP in terms of including all of the effects, but they do enable you to put the surface features in terms of either a spherical harmonic model in Starry or a Gaussian process on the surface of the star in Spotter, which paves the path forward for doing inference problems with this. Anyway, we have this picture that we have been using for quite a while of the underlying stellar surface. But how can we use it or incorporate it into our methods? An example of this is the FF prime method by Suzanne Aigrain. So Suzanne was starting from photometry, actually, but she used the basic geometry of putting a spot onto the surface of a star and having it rotate across to write down the equations that govern the signals that you would see in RVs. And from that beginning in photometry, it's been generalized by Vinesh Rajpal to use different activity indicators in the spectrum that trace different aspects of the spot signal. It's also recently been adapted by Hao-Chuan Yu in a recent paper to work across the full cross-correlation function instead of being limited to the RV time series and additional indicators. I'll point out here that ancillary data can be really helpful in breaking degeneracies and giving us more information about what the underlying stellar surface is doing. As I said originally, the FF prime method was meant to enable you to use photometry and RVs jointly. I'd point you to this paper by Quang Tran, which is a nice look at using simulated data with simultaneous photometry and RVs to do a principled comparison of different techniques for this and show what the possibilities are. I'd also remind you of Rachel Rotenbacher's talk earlier this week about using interferometry. So in addition to light curve inversions, it's really exciting to think of being able to actually have an image of the stellar surface to include in our models. You don't actually need ancillary information to get some picture of the stellar surface. So the field of Doppler imaging goes back quite a while. I'm showing you here a figure from a seminal paper by Steve Vogt et al. In which they demonstrate their technique by doing a Doppler imaging of the Vogt star. And inspired by this, we did a loving homage of the spot star in this paper by Rodrigo Luger, which develops a Doppler imaging type of approach within his starry framework and tries to do full inference of the emergent spot spectrum and the quiet star spectrum along with the map of the star. regardless of how you approach it, Doppler imaging is extremely demanding in terms of the data quality and quantity that you're getting. And it's debatable whether or not we actually need to explicitly model the surface of the star here when it's only some projection of that actually feeds into our data. Maybe what we need here is not to fully parameterize the surface of the star, but to kind of use the idea of the coherent surface as this latent process that's shaping our models. That's basically what FF prime is doing, and other models too. Lily Zhao showed recently that if we kind of follow this intuition of the surface of the star being inherently low dimensional in the sense of it's a quiet surface with a few discrete types of inhomogeneities with their own spectra on them. That means you could call it compact and coherent in time. And that means that the model that you use to solve for it also must be possible to have a low dimensional model here. And I'll speed up a little. I'm running a little low on time. Right. The last thing I want to point out, we were talking about using the physics of the stellar surface, the picture of the star as an actual object. We can also use the physics of the stellar atmosphere. I think this is a really exciting emerging area that hasn't been looked into so much until the past few years. Some examples of what I mean here by using the physics of the stellar atmosphere include really nice work by Khaled Al-Mulla et al., looking at this line-by-line radial velocity approach, actually making it more of a pixel-by-pixel RV approach, and categorizing the different parts of the spectrum by the temperature of formation, so kind of the layer of the atmosphere from which the photons in that bit of the spectrum are coming. I think this is a really exciting and promising way of using lots of information from the spectrum, not throwing much away, but also kind of categorizing them using a physics-informed model here. Michael Palembo has done work tuning bisector diagnostics based on the extensive information we have on the bisector behavior of those individual lines in the sun. And finally, I thought a really clever thing was Shahaf and Zaki's recent work with a linearized model where essentially they're fitting the spectrum as a combination of a few different basis vectors, eigenvectors, whatever you want to call it, where the eigenvectors are set by the spectrum from a Phoenix model and the derivatives of that spectrum with respect to the effective temperature. I think this is really clever because essentially when we're looking at certain surface features, we are looking at a localized change in the temperature of the star. And I think there's, that is an oversimplification. There are other things that we can do here, but I really like this general idea of moving in the direction of using the work that has been done for many decades on the physics of stellar atmospheres and trying to really incorporate that into our models. Okay, I've gone through some of these big themes. Hopefully that's given you a little more context for the state of the field. The last big picture point I want to make is that I've kind of been talking through a bunch of different methods that work at all different stages of the data. And Hao-Chuan Yu in his recent paper made this really nice point that essentially radial velocity determination is a dimensionality reduction process. And we have a choice at which point in that dimensionality reduction process, from the spectrum to the cross-correlation function to the extracted RV, we want to work. There is this picture that while we lose information by going to the cross-correlation function and then the radial velocity, we're in some sense like gaining signal because we're not gaining signal, but we're able to work at lower signal to noise. And I do want to kind of push back on that. Because we're not gaining signal, you don't create signal from anything. So there isn't really, in my mind, an inherent reason that working in the full spectrum must be more demanding in signal to noise. I would think of it instead as we have these continua of where in the data space we're working. We also have a choice to make in terms of how much are we doing data-driven versus physics-constrained. Basically, like how many free parameters do we have? How much freedom are we giving to the model? How structured are we making it? And because a lot of the full spectrum things to date have been in the data-driven regime, we sort of conflate them. But I think that maybe where we want to be working is more in the physics-constrained full spectrum analysis, where we're not losing a lot of data, but we're also not in the regime of having to get extremely high signal to noise. So I'm just going to blaze through this. I said that we want to incorporate more stellar physics. What are the prospects for doing that? One point I want to make is that more recent EPRV missions on very large telescopes have opened up more possibilities or more practical possibilities for doing astroseismology, and I think we should take advantage of that. I'm excited about these continuous coordinated observations of various stars, as Neve and Arvind were speaking about. And I'm also excited about spatially resolved spectra on the sun with the POET spectrograph, or POET solar telescope at Espresso, and coming from star spot crossing observations, which we're going to hear about more tomorrow. But as my takeaways, I think we're working hard on this problem of teasing out stellar signals. I think there's a lot of really cool results happening all the time. It's an exciting thing to keep an eye on. And I think that we're going to end up getting a lot of new stellar physics out of this. So happy to take questions.
That was an excellent overview, Megan. Jennifer Burt from JPL. So you pushed all the way on your last quad chart to the left of talking about using the full spectrum. Do you see any value in going even a step further back and using the full 2D achelogram and or in, bringing in information from like the headers of our FITS files that contain things like the pressure and temperature values that Zoe was talking about earlier this afternoon as well?
Right, that is a great question. Yeah, so because I was really talking just about the stellar signal mitigation here, I didn't really get into the instrumental effects, which I think are still below the threshold of stellar signals in most cases. But yeah, as Zoe very convincingly showed, we do gain a lot from including not only some underlying model of the star, but also some underlying model of the instrument there. So yes, I think going back to the full CCD may be the future in some ways. I think also taking advantage of the fact that we have the same instruments observing many of the same stars repeatedly and kind of using larger hierarchical models of the full data set of an instrument is promising. I think that there's a lot of stuff that we can do to tackle instruments as well.
One more time. There's a question in the back.
Hi, nice talk. Harshita from University of Chile. I was just curious, in one of your earlier slides where you showed the discoveries, I just noticed that between 2010 and 2015, there are a few outliers. I was just curious about them.
Sorry, which slide was it?
I think it was the very first slide about the RV discoveries.
Okay, yeah. You get to revisit all my memes.
Yep. So there are like 5 outliers between 2010 and 2015. So that.
I'm actually not sure. Somebody from the Exoplanet Archive should answer this. I didn't constrain this plot to be discovery method of radial velocity. So it might be that these are like things that were strongly constrained by other methods. I didn't cut on the precision of the measurement, yeah.
I think we're actually out of time on questions. So maybe if you could ask after or in the Slack. And I think we have some announcements, so I'll hand it over to David. Thank you, everyone.